This video covers friction. A few things about friction. Friction is resistance to motion, so it's always opposite the direction of motion. Or another way to think about it, if an object is at rest, is if there were no friction, where would it move? Also, friction is always parallel to your surfaces, and we're going to be dealing with two types of friction, kinetic and static. So the coefficient of kinetic friction is less than the coefficient of static friction. So if you think of inertia, it is easier to keep something moving than to get it to begin to move. With static friction, if you have an object and you apply some force to it and it is not moving, there must be some friction. If you apply a larger force and it's still not moving, then the friction is also increasing in proportion to that. So with static friction, our first equation is an inequality, meaning that our static friction is less than or equal to our coefficient of static friction, which is represented by a mu, which is this Greek letter here, times our normal force. Remember that normal force is not always equal to just mass times gravity. Remember that on an incline, that could actually be equal to mass times gravity times the cosine of theta. So if you apply a force and it is not moving, then there must be friction. If your force increases, then the force of friction is also increasing. So you can increase this frictional force until a certain point where we reach our maximum static friction down here. So when you reach your maximum static friction, meaning that your object is just about to slide, then you can set it equal to your coefficient of static friction times your normal force. So I want to stress these 2 points. To solve for maximum static friction, the object has to just begin to slide or move. So you'll see this phrase in a problem, if it's hinting at you, then it's asking for maximum static friction. And all other times before that, you must use the sum of the forces equations to solve for friction. And what I mean by that is when we write our sum of the forces, we're writing all of the forces in the x direction, all the forces in the y direction. In this problem, a 1 kilogram book is held against a wall by pressing it against the wall with a force of 50 newtons. What must be the minimum coefficient of friction between the book and the wall such that the book does not slide down the wall? So always we start with a free body diagram. I know I have a force being applied to it, meaning that my wall is providing a support force, so it's my normal force. I know that this mass also has a force of gravity acting on it. And I need to have a frictional force opposite in the direction that it would be moving if there were no friction. So then we write our sum of the forces for both objects, for both directions. So in the x, I have my force applied minus my normal force is equal to 0. Because again, my object is at rest. Or I want it to be at rest. The sum of the forces in the y direction give me friction minus m1g. Again, is equal to 0. So what the problem is asking for is the minimum coefficient of friction between the book and the wall. I know that my friction needs to be less than or equal to my coefficient of static friction times my normal force. So all I need to do is replace all of this with information that I know. I know that my normal force is going to be equal to my force applied. So I can replace the n down here with an f. And that my frictional force in this case will be equal to my mass times gravity. So again, I can replace that down here. When I rearrange everything, I get mg divided by f is less than or equal to my coefficient of static friction, meaning that this number that I get here is the minimum that my coefficient of friction needs to be in order for this situation to be true. Anything larger than this means that I'm going to continue to be at rest, but this is the minimum it needs to have. Kinetic friction is a little bit more straightforward. Kinetic friction exists after sliding occurs. So this is when your object is already in motion. It is, for our problems, going to be independent of the applied force or the speed of the object. So this will always be true. This is not a number that varies. So our kinetic friction will always be equal to our coefficient of kinetic friction times our normal force, which is our equation here. So when you're drawing your free body diagrams with friction, you need to make sure you understand what direction my object is moving or would be moving, and then decide your direction of friction from there. So if we are sliding down a ramp, then my frictional force will be up the ramp, opposite the direction of gravity. If you are sliding up the ramp, well then my frictional force will be opposite of that. Again, from your free body diagram alone, you cannot tell the direction of motion. All you can tell is the direction of acceleration. So here we have a pulley system with friction involved. It says that mass 1 is equal to 20 kilograms located on a rough incline, and it gives us a coefficient of static friction and a coefficient of kinetic friction and an angle. It is connected to mass M2 by a string which passes over a pulley. So the first part asks me to determine the largest possible mass that will keep the system stationary. So if I'm just looking at my system, I want to draw my free body diagram. So I have M1G go downwards, tension go up, normal force is perpendicular, and friction will be going down our ramp. Here we have our second object with a gravitational force and tension going up the ramp. Again, I know that friction is going down the ramp because if there were no friction, then my object would automatically accelerate in that direction if I'm increasing the mass of M2. So I'm going to guess that my acceleration is going to be positive in this direction. Again, in this particular system, it really doesn't matter because our equations are all going to be stationary. So then I can write the sum of the forces, making sure that I make M2G positive and tension over here positive. Everything else, like mg sine theta, will be negative. So my two equations look like m2g minus t is equal to 0, and t minus friction minus m1g sine theta is also equal to 0. So then I can make a substitution for tension into my second equation. So that looks like m2, actually it's not 2, t is equal to m2g. So m2g minus friction minus m1g sine theta is equal to 0. Again, I'm trying to solve for mass 2. So I want to get mass 2 by itself. So I'm going to move everything to the other side. And then to be a little bit more specific, I'm going to say, well, my frictional force is dependent on my normal force times my coefficient of friction. Now this is a mu plus m1g sine theta divided by g. Now again, I want to put it in terms of things that I know. The only thing I don't know here is my normal force. But if I go back to my free body diagram, I can see that my normal force will be equal to, my normal force is upward, downward is my m1g sine theta, cosine theta, is equal to 0. So my normal force is actually equal to m1g cosine theta. So I can go back to this equation and finally plug in all of my values that I know. So this is m1g cosine theta plus m1g sine theta and I need to add a mu here, all divided by gravity. And this will be equal to mass 2. When I plug in all of my values, I should get a number of 16.8 kilograms. So the reason I was able to make this substitution here was because I was looking for my maximum. Now part B asks us to determine the tension in the string. Well, if I know that my mass 2 is 16.8, well then I can just go back up here and say 16.8 times 9.8 gives me 164.6 newtons. Now, part C asks us to determine the speed of the mass m1 at the bottom of the incline, at the bottom of the 5-meter incline. Now part C asks us to determine the speed of the mass m1 at the bottom of the 5-meter incline. So here, our string has been cut. So this part no longer interests us. We are only concerned with this part now. So if I redraw my free body diagram, I know my force of gravity still acting downward. My normal force will still be perpendicular, but now I know my object will be sliding down the ramp. So I have a frictional force now going up the ramp. So because we are starting a new free body diagram and basically a new situation, I can actually change my direction of positives and negatives, because we always want to make sure that it's in the direction of motion. So I know that it's moving down the ramp, so it's convenient for me to set it down the ramp. If you had done this at the beginning, everything would have been the same. Your signs would have just been flipped, but everything should have, nothing else should have changed. So here, I have m1g sine theta down at the bottom, and I have mg cosine theta here. So if a problem is asking for us to solve for the speed, you can kind of get that hint that we're going to eventually be using kinematics. But in order for that to happen, I need to have an acceleration. So if I write these sum of the forces, I have m1g sine theta minus my frictional force is going to be equal to mass 1 times acceleration, because I know my object will be accelerating down the ramp rather than moving at a constant speed. So here, my friction is now kinetic friction. And we only have one equation for kinetic friction. It is coefficient of kinetic friction times my normal force is equal to mass 1 times acceleration. So again, I made that substitution because I know that's what eventually is going to be happening. I had to redo this because my coefficient of kinetic friction is less than my coefficient of static friction. So we have all the pieces of information. All that we're missing is my normal force. But like we said before, my normal force is simply going to be equal to mg cosine theta, because I know my object is not accelerating in that direction. So if you wanted to prove that to yourself, then you can write the sum of the forces in that direction, and I know normal force goes upwards, mg cosine theta goes downward, and because it's not accelerating in that direction is equal to 0, so my normal force is equal to mg cosine. Now that I have all these values, I can calculate my acceleration. And then if I know acceleration, I know displacement in the x direction. I can assume that my initial velocity at the top, before my string was cut, is equal to 0. Then I can solve for my final velocity. So for acceleration, I get 4.33 meters per second squared. And then again, I want to use a kinematic equation. Final velocity squared is equal to initial velocity squared plus 2a delta x, where initial velocity is equal to 0. Therefore, my final velocity is equal to 2 times 4.33 times 5, which gives me a final velocity of 6.58 meters per second.